All right, second method of analysis for the solar cell performance characteristics requires you to actually collect the current voltage curve. This allows you to directly measure things like fill factor and efficiency rather than making approximations. So you're going to use one of these potentiostats. There's a few of them. They look nominally like this. There's a cart, and you'll turn on the power to the machine, to the computer, make sure both the monitor and the tower are on, and then power on your unit by clicking this button. And then open up the software, which is the CHI icon on the desktop. Now we need to connect our wire leads to the solar cell. There's actually 4 leads. There's red, white, green, and this black one. The black one doesn't need to be connected to anything. And so you can see here that I actually have the white and the red leads, which would be the reference electrode and counter electrode in electrochemical speak, and the working electrode connected to the other pole here. So these are shorted together. You can connect them in any way that makes sure that they're touching, and then the working electrode is isolated over here. We're going to put this on our plastic plate here in the center, just like we did before, and then you'll have to get this to stay in position so that the electrodes don't pull. You can do that with a ring stand and a clamp. You can do that with a piece of tape, whatever way you need. Just make sure that's secured in space. Okay, so once you have the piece of software open and you have your solar cell wired up correctly, the next thing we want to do is measure the open circuit voltage so that we have a starting point for our IV curve that we're going to scan. So the actual software may look different. We have a few of these potentiostats around with different versions of software, but they'll all be nominally the same. So first thing you do is click the T button, that's for technique, and then you'll be provided a bunch of pre-listed programs for different electrochemical techniques, and you're going to need to navigate down, it's typically at the very bottom, to this parameter called open circuit potential time. You'll click OK, and that'll open up a dialog box where you can put in the parameters for this open circuit potential time experiment. The default's always going to be 400 seconds, which means you're going to measure the voltage for 400 seconds. That's way too long. So normally like 10, 20, 30 seconds, somewhere in that range is more than enough time to measure the voltage. And then you can leave these other parameters the same. You'll click OK and nothing will happen until you click the play button. And so now that we've chosen the technique, we've loaded the parameters of the technique, that's queued up, you'll press play, that'll start measuring the voltage. So at this point, if you're in the dark, you can start your experiment, but that won't be the open circuit voltage in the light, that'll be the open circuit voltage in the dark. And so we want the open circuit voltage in the light, so you'll flip the lamp on, press play, and then see what the voltage is. By the way, this is the equivalent of measuring this with a multimeter and just connecting the two contacts across the multimeter. This is the same thing that you're doing here. You can see now that I'm measuring potential on the y-axis, and I'm measuring time here, and I can see the red line that's populating at the bottom. And it's near 0 because we don't have the lamp on in the background. So if we swing over here, turn the lamp on, now we illuminate our cell, and you can see a very large step in the voltage, the photovoltage. So here's our baseline, here's the voltage when the light is on. Why that's useful and why we want to do that first is because it gives us a starting point for how we want to scan the voltage and measure the current in our IV curve. So you can see I can hover around this line. This is where our photovoltage was, and at the bottom here it'll tell me that the voltage is about 0.451 volts. So I want to remember that as I set up my next experiment. After getting the open circuit voltage, now we can actually conduct our IV scan, which means we're going to vary the voltage and measure the current at the same time. That's the IV curve. So that's a different technique. So we go back up to our T, and from this series we'll choose cyclic voltammetry. That's usually towards the top of the list. Click OK. That'll populate a new set of parameters here. So the first parameter here is init E in volts. That's the initial voltage. So when you're scanning the voltage, this is your starting point. What's your very first voltage point that you're going to apply to your solar cell and then measure the corresponding current? This is what we want to set as our open circuit voltage, because that What we don't want to do to any system is apply a voltage where we have a lot of current flowing right away, because that's pretty far from equilibrium. And so we know the definition of the open circuit voltage is the voltage when there's zero current. And so we just measured that as the open circuit voltage. And so we can pop in what we just measured, that's our VOC, as 0.45. That means that's our starting point. So no electrons will be flowing at the open circuit voltage, and then we can scan away from there and start to draw current. That's a much safer way to do this rather than just start in some arbitrary place. High, in this case, the high voltage or high E potential refers to the positive direction, high in terms of more positive than this voltage. So from 0.45, if we moved into the positive direction from that, we don't actually need to scan in that direction at all. So we're gonna capture this, because remember, we're gonna want to scan in the direction where the current to the short circuit current, which is going to happen at 0 volts. And so we'll pop in a value for this one at 0, since the short circuit current is defined as when the voltage is 0. So what we're essentially doing is scanning between our two limiting bounds, our open circuit voltage and our short circuit current voltage, the voltage at which the current is short circuit, which is 0. So that's the range we want to scan. On our scan polarity, we can choose either the negative or positive direction. We want to go negative because we're starting at 0.45 and we're actually not going positive with that at all, right? So it wouldn't make sense to go positive. So it's going to scan backward from 0.45 in the negative direction towards 0. A good starting scan rate, this is how fast you're sweeping the voltage per second, is 50 millivolts, which is the same as 0.05 volts per second. The sweep segments are how many times you're going between the high and low potentials. And so in this case, we're starting at 0.45, we're going to 0, and then we're going back to 0.45 if we have two sweep segments. If we only had one, it would only go in one of those directions, 0.45 to 0, and then it would stop. Typically, we're talking about 1 or 2 scans, no more, because we could start to damage the cell. We'll keep the sample interval at 0.001 and the quiet time as 2, and the sensitivity is going to be a variable that you control manually. For the silicon solar cell, for the 1 centimeter squared silicon cell, we're going to pop this up to 10 to the minus 2 because we expect around that much current to flow in amps, so around 10 or 20 milliamps. So you're choosing a sensitivity that's roughly the same as what the current is you'd expect. And so if you have no idea what this is, then you can start with a high value. And you can talk to me about this. One other note is that some versions of the software will also have 1/4 step here called final E. And so if your machine has that, then choose 0 as your final as well. So it would be your starting potential, 0, 0, negative. Okay, then you can click OK, and just like before, that stores our experimental parameters, but it won't initiate until we press play. To measure the dark scan, how does this thing behave in the dark, which is essentially just like a diode, then we can cover our cell. We can come back over to the experiment that we set up. We already programmed the parameters, so we can just press play. We may override data. And we can see it's scanning from 0.45 down here out to 0, and we can see the diode behavior that we'd expect. The timing for the experiment is up here, so now it's turning around for the second sweep segment. And we'll finish, and then I'll show you a trick to scale this so that you can see it nicely. So there is our dark IV curve. All right, to take the lighted version of the IV curve, then of course we turn the power on to our lamps, and then we rerun it. Gives us a graph that looks exactly the same, but now it's been shifted. And what I can do is choose graphics, new overlay plots, and I can select a couple different plots, just say this dark and this light one here, and I can overlay them at the same time. All right, cool. So we've got our dark curve down here and then two different versions of the light curve up here, just two different runs. So you can see the big step, that's our photovoltage. So if we want to find the open circuit voltage, we know that that's the voltage at zero current. And so if we go to the zero current here, where that intersects, that's our photovoltage, which makes sense because we'd already measured it to be around 0.45. So there's our VOC. And then short circuit current is the current at zero voltage. So we'd go to zero voltage here, and we'd go up to whichever line we're trying to measure here, and we would see where it crosses that axis. And we can do that by hovering here, but we can also export this data, which is perhaps more useful. How to export data from the CHI potentiostats to a text file so that you can process that data in Excel or any other data processing suite. You go to File, and you go to Convert to Text over here, and then you choose any of the raw files that you want to convert to text. And what's nice is you can just convert all of them at once. If you've got a folder of data, you can highlight all of these files, which are bin files that can only be opened and processed in this software. So if you want to process it in Excel, you need to convert it to a CSV file. So you click Open, and that's it. If you open up that folder location now, each one of those files will have an identical file name along with a text file.